Okay, sweetie. So what's your ETA? 10:21? Okay, perfect. Yeah, but as soon as you exit Corpus, shoot that down. But otherwise, I'm glad you're going back home. I missed you, love. Mostly overnight. I said I missed you. Mostly overnight. I missed living next to you. Huh? Yeah. Haha. But it was an easy sleeping with your family, that's for sure. Anywho, sweetie, I definitely can't wait to see you. So I'm happy that you're on your way home.
Can you all hear me? Someone say something.
Can you hear me?
Yes, I can hear you. Thank you.
Nope.
I just need, because, yeah. It shows up the microphone's not working, so I changed the microphone, I changed back again, and I don't know if it's working or not. It's come to my attention through more than one avenue that oh, let me do this real quick. All right, continue on with my freaking little thing. Stupid. They got these wonderful machines in here for the computers, for the classroom computer. And yet, these computers, the settings for the touch screen haven't been set correctly. So when I touch the screen, it's actually about almost 1/4 of an inch to the right of where I touch the screen. So if I don't remember that when I touch the screen, then I go someplace I didn't need to go. You're doing complex numbers, right? The complex one.
509.
5 what?
Oh, no.
509. All the way back there.
I think.
Or 609.
Yeah, I'm wrong. That was some other notes. We are on 594.
994. Oops, need that. There we go. Okay. In the syllabus, which I need to change, I had the final exam day, the next exam day being next week. We have 2 weeks between Thanksgiving and finals week. So I'm gonna put the third exam after Thanksgiving. So you'll have the review and the final, and exam 3 the week after. The week after Thanksgiving. And so that'll leave us 2 days to review for the exam. I like to do that. And if there's any additional material I want to cover, that will be done on the Monday after Thanksgiving, but that Monday of that week. Yeah.
So we're gonna review the week, Monday, the week after Thanksgiving. Or
Yeah,
third test?
for the third
Or
test.
third test can be on Wednesday.
Yes. Yeah, I try and do it that way. So that means I need to get the review up before Thanksgiving. All right, had we done this screen?
No,
Okay, so we're gonna, yeah, we're gonna plot this point. No. So, for cosine pi over 3 plus I sine pi over 3 is the same thing as 4 cosine pi over 3 plus 4I sine pi over 3. And so what's the cosine of pi over 3? Unit circle. What's the x and y of this point? So cosine of pi over 3 is 1/2 plus 4 times I, and the sine of that point is the square root of 3 over 2. So this is 2 plus 2 square roots of 3i, or 2i square roots of 3. So this is my x, and this is my y. So this is rectangular form. And I like to convert it to rectangular form to graph it. So 2 units this way. And then 2 times the square root of 3. The square root of 3 is approximately 1.7. And 2 times 1.7 is approximately 3.4. So just under 3.5. So that's going to be here. And that's the point. And this angle here is pi over 3. That's how I typically do it, is to convert. I have it in polar form, so that's easy to convert to rectangular form. Well, the radius is 4, and the angle is pi over 3, so that means this distance here is 4. And this is 2 square roots of 3, and this is 2. Is that right? To write it in polar form, yeah. Polar form is just 4 pi over 3, which is what they have there. And so if you wrote it in polar, using the polar coordinates, or the rectangular
would it be 2 for the x-axis, or how the graph shows it in the?
oh, yeah, that's 4 times 1/2, which is 2. Yeah, that would be 2. Well, let's see. What they do here. Yeah. Same thing I did. Oh. Why minus? Why is it minus?
No.
That's a typo. swear these people don't look at the PowerPoint that they put out. So yeah, this is they're this actually looks like a 45-degree angle. It's not a 60-degree angle. It would be more like this up to here. It's not up that high, but up to here. And so, yeah, this would be 2. And this would be 2 times the square root of 3. Two squared is 4. Okay. And then I have 4 times 3, which is 12. And that gives me the square root of 16, which is 4. Yeah, so that does work out. Okay. And so my only issue here is that they changed that plus to a minus. That's an unusual typo, but when I change signs, it's usually changing a plus sign to a minus sign. But yeah. Okay. All right, suppose that z sub 1 equals r sub 1 e I theta sub 1 and z sub 2 equals r sub 2 I theta sub 2. So you have 2 different, well, the r sub 1 and r sub 2, they could be the same number. Okay, so don't. So it'd be like if you squared a number, and this is gonna be what happens. You end up multiplying the 2 radii together, and you end up adding the 2 angle measures together. Because you're just using the properties of exponents. When you're multiplying like bases, you add the exponents. So this is I theta sub 1 plus I theta sub 2, and all they did was factor the I out. So all you need to do is add the 2 angles together and still multiply by I. All right. And when dividing, when you convert it to exponential form, then you're just following the rules for exponents still. You divide the coefficients, right? Because those are just constants. And then the exponents you subtract. So that's going to be I theta sub 1 minus I theta sub 2, because that's in the denominator. And then you just factor I out. And so all you're going to do is subtract the 2 angles in the appropriate direction. With subtraction and division, the direction in which you do it is important. Not so much with addition because of the commutative property. Yesterday I went racing in the house and left my coffee and another drink sitting on the counter. So I started my morning class in cafe.
You make the coffee at home?
Yeah.
Oh, I thought you bought it.
My daughter bought a Keurig. I didn't used to drink coffee, and I started drinking those mocha frappes from Starbucks. And then I started drinking them, whatever the version they are that McDonald's had. And then my daughter just, well, that's just coffee and milk. And so I started making it myself at home. And then I started decreasing the amount of milk. And then I just put sugar in there, I'm good.
So I've always liked the smell of coffee.
Maybe.
It's just the bitterness, the bitter taste, and so that's why I put 4 sweeteners in there. All right, so we want to multiply these two together and then divide them. So we're gonna use that, we're gonna convert it to exponential form. So z is 2 times e to the I 2 pi over 9. And and then the other z. Oh, no, this should have been a w. Photo hands. I'm gonna start referring to the I, and then we're gonna add 2 pi over 9 to 7 pi over 18. Yes, you're at a point in your mathematical career that adding and subtracting fractions should be secondary to you. It should just be, yeah, it's not hard. So this is going to be 4 pi over 18 plus 7 pi over 18. I multiplied the 9 by 2 to get an 18. So I need to multiply the 2 in the numerator by 2. So then I just add the 4 and the 7. And so that's going to be 11 pi over 18. So 11 pi 18. When you multiply. When you divide, well, I already converted the z angle to having the same denominator as the w angle. Where multiplying, you added the 2 angles. When dividing, you're subtracting. And since z is on top, we subtract the z angle argument is the argument of z, because if it's the angle, then it's called the argument of z. So the argument of z minus the argument of w. Since that's the direction of the division, that's going to be the same direction of the subtraction. So this gives us a negative 3 pi over 18, which is a negative pi over 6. And a negative pi over 6 is the same as 7 pi over 6. And I'm just going to be interesting to see which angle they use. And then for r, it's just going to be the 2 divided by the 3. So this is going to be 2/3 e to the I times a negative pi over 6. I think that's what they use, if I remember correctly. Oh, Klutz. Near as klutzy as my older brother used to be. Oh, and then I think they're going to convert it to, well, if you convert it to polar form. Then it'll be 6 times the cosine of 11. Are they asking us to rewrite it in polar form? Let me go back. No, they're not. But since they start out in polar form, the expectation is that you end up writing them in polar form. And so they got the same thing doing the multiplication. Adding these two angles together means I need to change this one so it has an 18 on the denominator. And yeah, they rewrote it in polar form. So the radius is 6, the angle is 11 pi 18ths. And so we would do the same thing with this one, where 2/3 on the outside of the parentheses and inside you have the cosine of a negative 11 pi over 6 plus the sine of a negative pi over 6. And then you use the even odd nature of those angles of those trig functions to rewrite it. Yeah, let me do that. So we get 2/3 cosine of negative pi over 6 plus I sine negative pi over 6. Okay. Cosine of a negative angle is the same as the cosine of the positive of that angle. And sine of a negative angle is the negative of the sine of the positive. And we want to try and write our angles as positive in the sine outside, and the sine of it tells us, are we going along that angle or are we going in the opposite direction? So the division, yeah, so they end up subtracting like I did here. And they end up with the same thing I have over here, I have here. And then writing it in polar form, and I think they continue on, yeah. And then they correct for, well, oh no. They convert, okay, I can see that, I see what they did. Because 11 pi, a negative 11 pi over 6 is the same thing as 11 pi over 6, right? Because negative pi over 6 is over here. But we're only concerned about where we end up, and so going around this way ends up at the same place. And the cosine of this angle and the sine of this angle and the sine of this angle are the same. So that's why, so okay. And sine is always negative down here, so that will end up giving us a negative value. Where sine of pi over 6 gives us a positive value, so that's why we're subtracting it, because it needs to be negative. So, yeah. Either way, either this way or this way is correct. If you left it this way, then that you might lose a point. Because it's not simplified. Simplified means you don't have any negative angles in there. So you rewrite the negative angle to the positive corresponding angle, or you deal with the odd and even nature of sine and cosine. And that's what I dealt with. I dealt with the odd and even nature of sine and cosine, where they just wrote the angle as a positive, the positive version of the same angle. argument of a complex number is periodic. Right? Because with this angle, remember, we just have some angle here. I can go straight to it, or I can go around once and come to it, or I could go around twice and come back to it. Or I could go in the negative direction. Let me get a different color for that. So I could go around once in the negative direction and then come to it. Once or twice or 3 times or 4, however many times. That's what the K is, or K is any integer. So being an integer, it can be positive or negative, and it can be 0. So when K is 0, we're talking about just theta. So if you want theta to be within a certain range, like sometimes they'll tell you what is this number what is theta between 2 pi and 4 pi. So that means you go around once. So that means you're going to add 2 pi to whatever you get for theta. So it just changes what it looks like. It doesn't change the end values. Because sine and cosine of pi over 4 are the same values as the sine and cosine of 9 pi over 4. Or 17 pi over 4. Or 25 pi over 4. Or 401 pi over 4. As you go around slowly, you go around 100 times. No, 200. You go around the circle 200 times, and then you go to pi over 4. You still wind up at pi over 4. All right. This is a name I cannot pronounce. De Moivre's, I don't know. De Moivre's theorem. I think it's a French name, so. But I think Euler, although he was from France, he was actually German by birth, or he could have been Italian by, I don't know. It was a long time ago. At a time when borders didn't mean as much as they do now as far as travel is concerned. Okay. Well, if you're going to raise a complex number to an exponent, so I want z to the 73rd power. So instead of writing multiplying 73 of these numbers together, I use this and then convert it to complex form, to rectangular form or polar form. So to show why this is true, we have z, which equals r e to the I theta. And we're going to raise z to the nth power. So I'm going to raise this to the nth power. Well, it's an n, not a 2, Thomas. Okay. So using the rules for exponents, everything in here gets hit with the exponent on the outside. So that's r going to be to the nth power, and then I multiply this exponent by n, and so that's going to be e I to the n theta, which is what they have there. And they're grouping the n and the theta together simply to say that these are two numbers that you multiply together, and then you have I. That makes it complex. I'm trying to remember the class I took where we went through the theory of how you can write a complex number in this form. But that was a long time ago. Yeah, early 90s. No, actually late 80s. Well, 89 to 91, somewhere in that period. So I went back to school. Yeah, I'm a classic late bloomer. I was around 35 when I finally got into my chosen profession. And n is an integer number. A positive integer number. So we want to write this in exponential form. So the radius is 3. So that's going to be 3e to the I, and the argument is pi over 6. And we're going to raise this to the third power. So I'm going to raise 3 to the third power, and I'm going to multiply pi over 6 by 3. So this is going to become e to the I 3 pi over 6. And that reduces nicely to 3 to the third power e to the I pi over 2. Well, now I can write this in polar form. I can write it back this way. So, well, first I need to evaluate e to the third power, which is 27 I to the pi, e to the I pi, or pi halves. Or pi I halves, or pi halves I. There's multiple ways of writing that. But anyway, the radius is 27. And so, and the angle, the argument is pi over 2. So it's cosine pi over 2 plus I sine pi over 2. Well, the cosine of pi over 2, all right, remember your unit circle, pi over 2 is a quadrantial angle, and this point over here is 0, 1. So cosine is 0, so this is 27 times 0 plus, and the sine is 1, so that's 1 times I, or just I. And so this is just 27I. Which is a pure imaginary number. Well, I think they actually write it this way as 0 plus 27I, and then they go to that. But either way. Oh, they didn't. Okay. Some textbooks do. They show that they do the multiply. They did, but I normally just do the addition because the x value, the real portion is 0, so there's no real portion, and so you only have an imaginary part. So we want to find out what's going on there with that point. Please realize, I am not raising the 2 to the 5th power. Correct. I would have to have brackets around that to say, so if it was written this way. Then the 2 is being raised to the 5th power, but it's not written that way. This eraser. Picking it up. So all the work here, we're going to look at that point. That point is here. 1 plus I. So we want to find out what R is. Well, that's 1 squared plus 1 squared, square rooted, so that's the square root of 2. So we know R is the square root of 2. So now all we need to do is find out what the angle is. Well, or do we really need to find the angle? Yeah, we do need to find the angle. So this is 1 and this is 1 and it's a right triangle. And so if this is theta, then the sine of theta equals 1 over the square root of 2, which is the square root of 2 over 2. What angle gives you the sine? In the first quadrant, what angle gives you the square root of 2 over 2 for its sine?
45.
45. So that's pi over 4. So now I have the pieces to write it in this form. So this is going to be 2 times the square root of 2 e to the I pi over 4 being raised to the 5th power. Which gives us 2 times the square root of 2 being raised to the 5th power times ei to the 5 pi over 4. The square root of 2 raised to the 5th power is the same thing as the square root of 2 raised to the 4th times the square root of 2. I just factored one of these square roots of 2 out. Because 4 is a multiple, because I can rewrite 2. The square root of 2 is 2 to the 1/2 power. And that's being raised to the 4th power. So that becomes 2 squared times the square root of 2. So this becomes 4 square roots of 2. So now I have 2 times 4 square roots of 2 times e to the I 5 pi over 4. And so this is 8 square root of 2 e to the I 5 pi over 4. 5 pi over 4 is, what is that, 225-degree angle? That's in this quadrant over here. So when I raise this to the 5th power, I wind up down here. And I've changed its radius as well. No, I don't change its radius, but then we're just gonna multiply that by 8, so it comes all the way down to here. Or further. So, and now to write it in rectangular form, well, first I want to write it in polar form. So that's going to be 8 squared to 2 times the cosine of 5 pi over 4 plus I sine of 5 pi over 4. Right, so since I know which quadrant this angle is going to wind up in, I know my sine and cosine are going to be negative. And so that's just the sine and cosine of pi over 4. So cosine is going to be a negative square root of 2 over 2. And sine is going to be a negative square root of 2 over 2. Still multiplied by 8 squared root of 2. And now I multiply in by 8 squared root of 2. And I'm going to migrate this negative sign out front. So this becomes a negative 8 squared root of 2 times the square root of 2 divided by 2 minus I times the same thing. 8 squared root of 2 times the square root of 2 divided by 2. That goes equal sign. Well, 2 times the square root of 2, so this becomes 8 times 2, and this 2 goes away with this 2. And the same thing happens here. So this becomes a negative 8 minus 8i. Yeah, if it's on the 45-degree angle, the absolute value numbers will be the same. It's just the signs will tell you which quadrant. And since they're both negative, it's in the third quadrant. And it's on a 45-degree angle, your x and y are going to be the same. In absolute terms. Oh, I see what they did. They didn't even look to see what the angle was. To write it in. Well, I don't know, they probably should change that. Okay. All right, they're saying that this ends up being the cosine of pi over 4. So yeah, so that's how they got the pi over 4. In a similar process I did, but anyway. Whoops. Let me erase whatever up here. It's in the way. Okay. Okay, so they wrote it in rectangular form, and then wrote it in polar form, and then they wrote it in exponential form. I think I kind of bypassed this part. But and then this is what we're going to raise to the 5th power before we multiply 5 with 2, which is what they're showing here. And so. Oh, yeah. I noticed this the other day, I just haven't been able to correct it yet. This is just, they missed the keystroke. And they didn't put it in as an exponent. So that 5 is supposed to be the exponent on the square root of 2. And so it becomes, and like what I had done, it becomes 4 square roots of 2 here. And this, the angle becomes 5 pi over 4, and then we're multiplying by 2. So this is it in rectangular form, I mean in exponential form. And then we go through and write it in polar form. And then converting that to rectangular form. Okay. They went with 1 over the square root of 2 instead of the square root of 2 over 2. Because it's the same number. It's just leaving it this way. When you multiplying by 8 square roots of 2, then the square roots of 2 go away and you're left with the 8. And you get the same thing I did, it's just one less step. Any questions so far? This isn't hard, it's not difficult, it just can be confusing. Trying to follow what you're doing and making sure you're doing it correctly. And so they just rewrote it without the polar coordinates and the standard form. Oh, no, but they wrote it in they kind of dropped this one and went straight to here. Because that's what they were asking. They were asking in exponential form and in rectangular form. They weren't asking for the polar form. But you kind of have to use the polar form to get to the rectangular form. All right, complex roots. W is the nth root of z . No, z is the nth root of w if z to the n equals w. Two is the square root if 2 squared equals 4, then 2 is the square root of 4. That's what they're saying here. So the nth root of w equals z. That's what they're saying with this definition. But I can write this using exponents, right? So this is w to the 1 over n. Well, I can use the what's his name's theorem here. De Moivre's theorem here. Because that's all this is. This is just the application of De Moivre's theorem. But there's an added caveat, because when you take the nth root of a number, of a complex number, you will have an n distinct number of complex roots. So if you're taking the third root, you're going to get 3 different points, 3 different complex numbers. I always think of complex numbers as points on the complex plane, which is why I keep calling them points. The nth root of r is r to the 1/2 to the 1 over n power. I multiply n by 1 over n, which is the nth root. And we're going to multiply by 2k. We're going to add 2k pi, where k, it goes from 0, is an integer number from 0 to n minus 1. So if, like I said, if you're finding the third root of z, then k will equal 0, 1, and 2. So you're going to add 0 to theta. You're going to add 2 pi to theta. And you're going to add 4 pi to theta. And then you're gonna multiply it by 1 over 3. Or you're going to divide it by 3. So you'll get 3 different angles here. So if it was pi over 4, then you would get 1/12 pi. Right, if theta equals pi over 4. And so that's going to be 1/12, and then this becomes what? 8. So that's going to be 9 pi over 12. I mean 9 pi. Yeah, 9 pi over 12, which is pi over 3. I mean, not pi over 3, pi over 4. And then that's this is 8, so that would be 16 pi over 2, pi over 4. No. This is 8 pi over 4, so it's 16 pi over 4, so I get 17 pi over 12. So I have these 3 different angles. And I wind up in 3 different quadrants, a third apart. So that would be 120, and then another 120, so it's going to be down here. So we have 3 points that are the same distance from the origin, from 0, but at 3 different angles, because I'm dividing this into thirds. That's what happens. So if it was to the 4th power, then we would have 4 angles. So actually, I have one of these is wrong. Because if it's 1/4, 4 over pi, and then 4 over pi, 4 pi over 4 plus 8 pi over 4, which gives us 9 pi over 4 times 1/3. Yeah, so I did that right. Get it right. Because this would be considered the z sub 1, I mean c sub 0. And then this one is z sub 1, and then this one is z sub 2. Because the sub depends upon what k is, 0, 1, or 2. So this would be the first one, this would be the second one, this would be the third one. Although the hierarchy doesn't match, there's no true hierarchy here. So we want the cube root of this. We have negative square root of 3 plus I. Negative square root of 3, so I'm gonna look at what quadrant I'm in. Negative square root of 3 is approximately 1.7, and positive 1 puts us about here. So this is the square root of 3, and this is 1, so what is R? 1 squared plus the square root of 3 squared, square rooted, well, what is that? That's gonna be 2, isn't it? Yeah. 2. So what's this angle? So we're gonna get, and that's negative, the negative square root of 3 over 2 is the cosine, and 1/2 is the sine. So on the unit circle, this point over here is the negative square root of 3 over 2 and 1/2. What angle is this? It corresponds with this angle over here. So it's one of these angles away from pi. The square root of 6. So this is 5 pi. So 5 pi over 6. I mean, pi over 6, not square root of 6. Pi over 6. So this is 5 pi over 6. So theta here, theta is 5 pi over 6. Well, you can use a calculator and do well, I would do it here on the negative of the cosine inverse of a negative square root of 3 over 2. So my R is 2, and my theta is 5 pi over 6, so I can write it in rectangular form right away, which is 2 times EI 5 pi over 6, and I'm trying to find the third root. Correct? Yeah, cube roots, so that's the third root. So we're going to be dealing with the cube root of 2, e to the I 1/3 times 5 pi over 6 plus 2k pi, where k equals 1, 0, 1, and 2. So we have 5 pi over 6 plus 2 plus 0. So that's for when k equals 0. And when k equals 1, we have 5 pi over 6 plus 2 pi, which is, so that's gonna be 12 pi plus 5, so that's 17 pi over 6. And then when k is 2, that's going to be 5 pi over 6 plus 4 pi. And 4 pi is 24 pi over 6, so this angle is 29 pi over 6. All right, 17 and 29 are prime numbers, so we can't reduce those fractions. So in polar form, I have the three points. I have z, oh wait, should it be, yeah, z sub 0 equals the cube root of 2 e to the I 5 pi over 6, and z sub 1 is this cube root of 2 e to the I 17 pi. 17 pi. Come on, Thomas, you can write it. 17 pi over 6. And then z sub 3 equals the cube root of 2 e to the I 29 pi over 6. No, I didn't multiply by 1/3, did I? I didn't multiply, so that's gonna be over 18, because I need, because I still need to multiply by the 1/3. I forgot that part. So all my denominators become 18. I can do that. 2 times 18 is 36, and all of these measures here are less than 36. So it is between 0 and 2 pi. And all of those angles are 1/3 pi apart. So 1/3 pi is 6 pi over 18. So if I add so they got the same value for the point for W as I did. And then they set it up the same. Oh, I like how they set it up here. So they went ahead and wrote each of these this way, but they should still get the same numbers I did. Instead of saying pi over 6 plus 2k pi over 2k pi, they converted the 2k pi to 12k pi over 6. And then they would just have to add the 5 plus 12, and then 5 plus 24. So they did the converting up front rather than doing it along the way as I did. And then they multiplied in by the 1/3, so the denominator is going to be 18 all the time. Unless you can reduce the fraction. And none of those fractions. So, and so they're using the same nomenclature, nomenclature, I can't say the word right now. Brain's not working that way. The same notation I did, Z sub 0. And they got the same thing I did here. 5 pi over 18 for the angle. And Z sub 1, and they should get 17 pi over 18 for the angle. R isn't going to change, R is going to be the same because they're all in the same circle with the same radius. And then the third one, yeah, we wind up 29 pi over 18. All right. Now we jump into the happy subject of vectors. I really enjoy vectors. The short and sweet of it, a vector is a directed line segment. So here I have a line segment, right? It starts here and ends here, and it's directed. It has length, which we call magnitude. Here's another vector. It starts here, ends here, and we put an arrow to tell us which direction it's headed. If you ever watched the weather in the newscasts or looked on the Weather Channel, and they talk about wind patterns, and they show a field of little arrows that change with the wind direction, those are vectors. And the length of the vector is how hard the wind is blowing or how fast it's blowing. So the vector tells you which direction and the speed of the wind. In physics, we can use this vector to represent force. All right, the force is going in this direction, and how hard is it pushing? It can denote speed, which direction you're going, and how fast. So, okay. But we're going to get into some basics of vectors. We graph vectors. Vectors have an initial point, and they have a terminal point, where it starts from, where it ends at. Right? A position vector. A position factor, all position factors start at the origin. And then we can talk about adding and subtracting vectors algebraically. When we talk about graphing vectors, we're going to talk about adding and subtracting them graphically. And then we're going to talk about adding and subtracting them algebraically. That it's relatively simple process. Vectors have an x component and a y component because you can put it on a coordinate plane, and the endpoint is the x and y. The beginning point is x and y, and to find the position vector, you're just subtracting the x's and subtracting the y's appropriately. Okay, and so when you add and subtract vectors, you're just adding and subtracting the x and y components. A scalar multiple, a scalar is just a number. 3 is a scalar. I'm multiplying by 3. I'm multiplying by a -3. I'm multiplying by 1/3. I'm multiplying by 17/23. Okay, so a scalar is just a real number. Multiplied by pi, multiplied by the square root of 17. 17 has been showing up a lot in my head. A scalar multiple is just multiplying this, like, I want three times this vector, so that means I'm gonna come down two more times. So it instead of stopping here, now it stops down here. So I'm just multiplying this by 3. Finding the magnitude, well, that's just the length here, so that's using the distance formula or the Pythagorean theorem. The distance formula is the Pythagorean theorem, and so that's all we're going to use to find that magnitude. Find a unit vector. A unit vector, that means its length is 1, like on the unit circle. All the radii on the unit circle is 1. R1. And hard to think of as a plural in a single term. Okay. And then find the vector from its direction and its magnitude. All right, I know its magnitude is 5 and it's at a 45-degree angle from 0. Or it's at a 120-degree angle from 0. Or negative 120 degrees from 0, and its magnitude is 5. So what is that? What is that terminal point? And usually when we talk about finding vectors and all this stuff with vectors, we're talking about position vectors. And then modeling with vectors, I'm not going to get too much into that because we're getting close to the end. In simple terms, a vector, I don't care about that, is a quantity that has both magnitude and direction. A directed line segment. It's customary to represent a vector by using arrows, which is what I have been doing. The length of the vector represents its magnitude, and the arrowhead indicates the direction. So you cannot draw a vector without an arrow at one end or the other. If P and Q are two distinct points on the XY plane, you have exactly one line that contains both P and Q. That's one of the basic axioms of or postulates of geometry, is that through any two given points, there is exactly one line. An axiom or a postulate is a statement that we take to be true. In other words, we have not proved it to be false. We can't prove it to be true. We know it's true. Visually, we can see that it's true. But there's no way to mathematically prove that it's true. So they're called postulates or axioms. And then there's a line segment where its endpoints are on P and Q. Now, for a vector, I can state where it starts from and where it ends. If I say the vector PQ, then that means I'm starting at P and I'm ending at Q. If I say QP, then I'm starting at Q and ending at P. So they'd be opposite vectors. Because they go in, they're the same length, but they're going in opposite directions. Ordering the points so they proceeds from P to Q results in a directed line segment from P to Q, or a geometric vector, which is denoted by PQ with the arrow this way. Now, in mathematics, it's left to right. If I wanted to talk about this vector, then I would write it this way, QP. The arrow is always going to the right when you write it this way. So the first point is the initial point. The second point is the terminal point. You would never write it this way. This is nonsense. You don't write it that way. Whenever I get to this section, there was a class I took where the professor had some points up there, and he was in part of the lesson, he said, well, give me the name of a point. And so Darla, she's a hoot. She said Q, right? And so give me another point. And she said T. And he said, okay, line 7 QT. And he stopped, and the whole class was laughing. Yeah, cutie. Oh, that was cute. Okay. So, and whenever I see the store QT, that's what I think of. The Darla. I haven't seen her in years. She used to teach at SAC, and she taught at Incarnate Word High School. And another friend of ours, McKenna, Paula McKenna, she's a professor at SAC. Yeah. They were good people. They were part of my group at UTSA. I got to finish my coffee today when I wasn't able to drink it yesterday. All right, so that's all this is talking about. P is the initial point, Q is the terminal point. The arrow in the drawn vector shows that. And how we write it notation wise, it shows that P is the initial point and Q is the terminal point. Okay. Vector V, notice the V is in bold face. What they used to do, and what I would do in my notes, since I can't do a bold-faced V, they would put an arrow over the top of the vector. I mean, over the. So this is vector V. Vector V, whose magnitude is 0. That means it has no length. Is called the 0 vector. Or the bold-faced 0, or in your notes, I would put an arrow over the 0. It's a 0 vector is assigned no direction because we're not going anywhere. I could be facing this way or this way or this way or this way. It's still the same spot. So yeah, I did my exercise for the week. Okay. Now, so 0 vector is assigned no direction because it's not pointing any direction, because it has no length to have a direction to go in. All right. Now, 2 vectors, V and W, are equal, written as V equals W, if they have the same magnitude and the same direction. So what they've done here, they've drawn 3 different vectors that are in 3 different places on the coordinate plane, but they have the same magnitude. Okay. And they're going in the exact same direction. They're parallel to each other. So if you drew the lines that connected those points, those 3 lines would be parallel, or they'd be the same line. Realizing that these could line up with each other. So if I move this entire vector over 1 unit, yeah, it's going in the exact same direction. Actually, I went too far over here. And this distance is the same as this distance. And same thing with these 2. If I move these 2 points this way, I wind up on the exact same vector. Okay. The sum of 2 vectors, that's putting one terminal end taking, here, we're gonna take the terminal end of W and put it, I mean, the initial point of W on the terminal point of V. And now the initial point of W and the terminal point, I mean, the initial point of V and the terminal point of W is the vector. So this vector is the vector W plus the vector, I mean, the vector V plus the vector W. They're calling it vector. Vector addition is commutative. So it doesn't matter which vector we start with, we still wind up at the same place. So these are two different roadmaps to get to point A to point B. I can go here and then over to here. So I go W and then I go V, or I could go V and then W. The blue vectors and the red vectors, what shape do they form? Not a triangle.
On
A diamond?
Well, mathematics, we don't have that shape. Well, that's only if B and W are the same length. A rhombus is a special case of this type of. You're used to seeing them being drawn this way, where these two sides are the same and these two sides are the same. Parallelogram. A rectangle and a square are special cases of a parallelogram. A rhombus is a special case of a parallelogram. Parallelogram is a rectangle that's been cut off, knocked off kilter. Although rectangles are parallelograms. Opposite sides are opposite, the opposites, I mean, yeah, opposite sides are equal and parallel. That's true with rectangles. That's true with squares. That's true with rhombi. A rhombi is what people traditionally think is the diamond shape. There is a mathematical shape that's a kite, which is the traditional shape of a kite, where the adjacent sides are equal. Two pair of adjacent sides are equal. Just like in mathematics, there is no such thing as an oval. It's an ellipse. We have circles and we have spheres. A spheroid, the planet Earth is a spheroid because it's not a perfect sphere. It's not a squash, it has bubbles. Okay. All right, vector initial, vector addition is also associative. So here we're adding three vectors, and notice we're adding the three vectors, the vectors are written in the same order each time. It's just we're grouping them differently. First, we're going to add these two and then add this one to it. So we're going to go from here to here. So the blue, yeah. Golly, trying to see how they're doing this. So the blue here is adding these first. So we get this line down here, and then we're going to add W to it. We end up with this vector, and then we're adding this vector to it. That's this one.
And the other one's on top.
Yeah. The other one's on top where we're going to add these two vectors,
Which is a black line.
which is this black line. And then we're adding this to this vector. So in both cases, we're starting with u. And then we're going to add the sum of these two together, which will put us here. And here we're going to add the sum of these two together first, and then add the third. So one, you're starting with a vector and then adding the sum of two vectors to it. And the other way, you're going to take the sum of two vectors and add the third vector to it. In any case, you're either going this pathway or this pathway, and you still wind up in the same place, just like before. But this doesn't form a parallelogram. This is just a quadrilateral. Quadrilateral just has 4 sides. And this is a convex quadrilateral because you don't have a concave side. The zero vector has a property that you add a vector to the zero vector, or you add the zero vector to a vector, you still wind up with that vector. We're just showing that this is a field or a group. It's a group. It's an associative group. It also has identity. Well, this is additive identity, and it should have multiplicative identity. If v is a vector, then the negative of v is a vector in the same magnitude as v, but is in the opposite direction. It goes the opposite direction. So this is the true definition of what the negative sign means. It means you're going in the opposite direction. What do I always say about negative? Negative isn't about the value, it's about the direction. You have negative cash flow. What does that mean? It's going away from you, not towards you. You have positive cash flow, means you have money coming in. Negative cash flow, it's going out. So that's the negative. That's the red in the ledger, where the black in the ledger is the money coming in. Okay. I took an accounting course, and that's all I remember from. Okay. It confused me so badly. I was one of these people who there's an old wives' tale that says education is wasted on the youth. Well, that's not 100% true, but I was someone who that's true for. I had no business going to college my first time through school, right out of high school. I should have gotten a job or something like that. I would have done well going into the military and getting some experience that way before I went back and got serious about school.
So I think we're out of time.
But, oh, okay, we are out of time. So next time we'll start with this, adding vectors geometrically. Well, the difference, the sum and the difference is adding the negative. So, yeah. Are there any questions? Let me. Move my camera. Yeah, Sebastian, I bet there's more than one person lost. Okay, vectors aren't too hard to deal with. It's just a matter of getting in there and playing with them. Thank you very much. We'll see you Monday.
Okay.
Yeah, we'll see how it goes on Monday about how far into vectors we'll have for the exam. We may not have too much about vectors on the exam. Which is a shame. I really like going into vectors. But that's me. We're at time, so unless you have questions for me, y'all are free to go. Okay, so what I'm gonna do is I'm gonna stop the recording.